exciting. So I'll try to write information here interesting to this side, up this end, and vice versa for that. So I'm going to say something about the KDV hierarchy. Then I'll describe a little bit about the moduli space of stable curves. Just enough for my purposes. But now the main aim today is to define a collection of cohomology classes in the moduli space of stable curves. I'll do some calculations, and so there is a case where they're non-zero. So no, always non-zero. Okay, and then I will assume I'll have time to give an application. So these classes will fit nicely with cohomological field theories. So in particular, Gromov-Witten invariance. So I'll describe that. Okay, so the KDV hierarchy. I want to get this precise. So a function u of for some reason I don't have the h-bar dependence, but a function of this sequence of variables t through t0 through t1 is a solution of the KDV hierarchy if they satisfy, well, I'm only going to write down one of them. This is the KDV equation. Yeah, so I'm going to write unimportant stuff at the ends. Okay? So I'll put more important stuff in the middle. I'm describing here the KDV hierarchy. Yeah, I understand that. I'm going to write important stuff in the middle. So you don't want, I mean, this is not important. This is KDV hierarchy, I think. Just know that it's over here. Where I start with an initial condition is just a function of this variable. And it's a hierarchy because I have dependence on the variables t0 through t1, t2, etc. And these are going to be further partial differential equations, which I won't write down. Okay, so the theorem, Koncevich-Witten, is that they produce a solution of the KDV hierarchy from the moduli space, from intersection numbers on the moduli space of curves. So if we define this to be the sum over all intersections with psi classes, I'll hardly define these. I'll define them a little bit in a moment, but of product with these variables. So this is equal to, say, t0 cubed on 3 factorial plus t0 cubed t1 on 3 factorial. So these coefficients here encoding these intersection numbers. And so the statement of the theorem is that this second derivative is a solution of the KdV hierarchy. With initial value is simply T0. So of course, KdV is taking some function and is just evolving this function with respect to time 0, evolving it with respect to time 1. So its initial condition is enough to determine the solution. Okay, so today my aim is to say something about another solution of the KdV hierarchy, known as the Bresson-Gross-Witten solution. So let me write this. So this produces a solution of the KdV hierarchy. So this, I'll give just the earlier terms and its initial condition. So the initial condition here is, so the claim again is that U equals H bar, the second derivative, is a solution of KdV hierarchy. Where now the initial condition is given by this function here. It's attributed to Bresson-Gross-Witten because they dealt with a unitary matrix model and produced this.
I don't think the first equation depends on H. Does it? Is it correct? There is no derivation of H.
Right. I'm just doing this to keep track of data. Stick it to B1 if you want. I actually like to keep track of it. So it's.
Okay, but then you write O of H squared.
Yeah.
I don't understand. It's a bit confusing.
Okay. Plus H bar squared times some stuff plus H bar cubed times some stuff.
And well, this stuff can be whatever. How can be equation?
Well, so it ends up that it's going to be some degree 0 function in these t's, but that's more information than I need to give. It's just, this is the initial condition, and it's going to be some nice rational functions which are degree 0 if I weight these correctly.
It's rational only with respect to
the Correct. So it's in fact homogeneous if I give that 1 minus t0 degree 1.
I think your question was that there is only one H bar there, but you've got all the other equations, the IR. So the other terms, they will depend on the other flags, T1, T2, and so on. So if you would put T1, T2, and so on equals to 0,
No, my equation is, I think, like, for example, let's say that H equals 1.
Just set it to be 1. It's actually not important H at all.
Can you write this function explicitly then? If H equals 1?
It's a power saving. You set that power savings to a value. We're looking for more solution. That's a formal solution in H bar.
Okay. Don't set it to 1 then. Right, so what I can do is I can just set some of the variables to be 0, set H bar to be 1. But the H bar is, can be removed. Okay, so. Okay, so the. Only this half of the room is discussing KdV. Fortunately, it means this half of the room is, does not need to be reading that. Okay, so the theorem that. Well, it's not a theorem as stated yet because I need to define something, but there will be a theorem here. And so the claim is that this, like the Kontsevich-Witten free energy comes from an integral over the moduli space. So again, just as I did before, I take the integral over the product of the psi classes And now I'll put a class in there. So as I said, so far I've stated this as a theorem, but the point of today's lecture is to define this class, theta gn. So the claim is there exists a collection of classes, theta gn, on the moduli space, such that this Bresengross-Witten free energy is given by these intersection numbers. Okay, so let me... Beg your pardon? Yep. Thanks. Okay, so... No. No, not at all.
It's different because it's the initial condition.
So yes, not at all. Okay, so the moduli space of curves. So this is the moduli space of stable curves with n labeled points. I won't really define this too much. I'll just give us some properties of this that I need. So there's some gluing maps. So I need to draw a picture here. So if I take this stable curve and take the final two labeled points and take this quotient curve, so identify these two, this gives me a map, puts this inside this space here. There's an entire fat modular space of these, so this gives me an entire fat space in there, and I'll give this the name rho. And similarly, where this has genus G1, this has genus G2. Again, I have an entire moduli space of these, and I take the last labeled point of each of these, identify them, and I get a stable curve. And I'll label this a little bit of abuse. I'll label this, say, phi, but I need to give you more information. I need to tell you which points are going where. So there's a whole collection of these, but it's not going to be that important. Okay, there's the forgetful map. Which forgets the final point and perhaps contracts some unstable components. And I have some line bundles, tautological line bundles. These are in Maxim's talk, the first talk today. The fiber is given by, well, one way to informally say it is the cotangent line at the ith point, the ith labeled point, and I want these cohomology classes. So psi I is equal to the first Chern class of this bundle, and it lives in H2. Okay, so that's as much as I'll need for the moduli space. And so now I'd like to essentially define this class. Okay, so this is a definition, but I need a theorem to say it's a definition. So just consider this sequence of classes satisfying, but in fact the theorem will be they're characterized by this, satisfying these four properties. So the first property is, sorry, this is in the moduli, the cohomology of the moduli space of stable curves. The first property is this is of pure degree. Pure cohomological degree. The second property is the most natural property we could ask for. We'd like the pullbacks to just pull back and give us the earlier guys in this sequence. So we'd like, say, rho star of theta gn to equal theta g minus 1 n plus 2. So the pullbacks, that's just a restriction. So inside mgn bar is this codimension 1, say, subvariety this mg minus 1 n plus 2 and restricted. When theta restricts to this, I want to get the theta that comes from that. Beg your pardon? Yeah, I'll need to give a theorem. But this is the assumptions. This will characterize it, what I'm saying. So it's just an assumption, pure degree. And I want to show with this assumption, you're going to be reduced to 2 possibilities. And 1 is what I'll be talking about today. And so I also want phi star of theta g. And the restriction of theta to this divisor is equal to these two n2 plus 1, where there's a little abuse here. I really mean I'm pulling these back from the projection maps, but that will do. Okay, and the third property, so the second property is the fundamental property. I simply want this class to restrict well. That's the fundamental property. Everything else I'm putting up here is extraneous to this second property. This third property is telling us how this class behaves under the forgetful map. And so when I pull back the class under this forgetful map, I'm going to, when I pull it back and I hit it with the m plus first psi class, that will be my class. Theta g m plus 1. And the final one is not really necessary. It's an initial condition. It just happens I need this particular initial condition. So theta 1, 1 is 3 times psi 1. Psi 1 is just a generator of the cohomology, okay, of H2. So this is going to be some multiple of the point class, and I want it to be 1/8 the multiple of the point class. In general, I would just take any multiple, but the theorem won't work without this. Okay, and so now the theorem. Correct. Just know that what you need to know is there's a theorem over here. Yeah?
Also, in the F you wrote, there's a linear and a quadratic term in 0, which contradicts your theorem. You subtracted those out.
In which this F here.
It begins what, 1/8 of T0.
Yes.
Oh, T0.
Yeah, that's exactly the.
Oh, this is genus 1 material.
Yeah. Oh yeah, there's going to be something that switches. Yeah. Okay. So, but what you've just noticed, what you've just seen is you've just seen that condition right here. Okay. Yeah. Okay. So the theorem is that theta gn exists, and here I need this, so I can use exactly these properties, and I could put a lambda times psi 1, and I can show this exists in genus 1, genus 2, genus 3, but I actually can't prove that it exists. So, and that's just because of the quirk of the construction. I wouldn't be surprised if it exists. But. Okay, and to answer Danilo's question, the degree is 2g minus 2 plus n. And this is a tau function. So this, let me now, yeah. So maybe I'll write it out. So exactly what's written already on that board there. Is a tau function for of KdV. Tau function of KdV. I don't know that. So the question was, is the class tautological? So I don't know yet. I produce it by taking a top churn class of bundle on the space of spin curves and pushing forward. So I'm actually not sure about. I know that question, tautological, I'm not sure about. Yes. Okay, so the first remark, maybe I'll put remarks here. Well, the first remark is this, is these intersection numbers, these are uniquely determined by these conditions, 1 to 4. So I don't know that this cohomology class that I construct is unique, but I can tell you the numbers I'm getting from it are. The second obvious property is that the genus 0 guys vanish. These genus 0 classes vanish. I've got the degree is 2g minus 2 plus n, so that has degree n minus 2. The dimension in genus 0 is n minus 3, so the classes vanish. What this says, so these classes are interesting to me for their relation with enumerative geometry. What it says is I'm interested in problems in enumerative geometry where the genus 0 terms vanish, invariants vanish. For example, covers of an elliptic curve, although I haven't got that example yet, but that's the type of. So it ends up that the topological recursion has already been shown to produce this. So there's topological recursion here, but. Oh, so no. What maybe you should have said is, what has that got to do with, say, a Frobenius manifold structure and a product? It's gone. There's no product in the Frobenius. What would be the associated Frobenius manifold? Well, you've got no product. In terms of the Kontsevich-Sorbelman Airy structures, the A term vanishes. But there are solutions still. Yeah. No, it exactly gets it right. So 2g minus 2 plus n, and then psi n plus 1. Oh, I'm sorry. Possibly what was stated then is that, let me just say something, where would it be appropriate? So theta gn lives in h to the 2 times 2g. I'm using half the cohomological degree. I think that might be your comment. Yeah, sorry about that. Thanks. Okay, and so now if I replace these conditions 3 and 4 by these conditions, theta g n plus 1 is simply the pullback of theta gn, and theta 1, 1, it's not really important, I'll just write it to be 1. This is exactly the trivial cohomology class. So these conditions, I want something of pure degree, the trivial cohomology class of pure degree. These restrictions, of course, this is a ring homomorphism. The pullback of the trivial class is the trivial class. And I've just replaced these. And so so this would imply that theta gn is just equal to the trivial class. So one message I want to get across today is basically there are two interesting classes out there, the trivial class and this theta gn. But I'll show that in part of the proof. Beg your pardon? No, it can't have been 0. That was Ezra's joke. It can't be 0.
If it is 0, then everything.
No, it can't be 0. It's that doesn't satisfy that last one. Okay, my plan was to use 8 blackboards, but alas. Okay, so I've promised not to put important stuff here, so I will put. Well, that's not important. What I'm going to give an idea of the proof, but what I'm not going to I'm hardly going to say anything about is the proof of existence. So the content of the theorem is the proof of existence and the relation to KdV. They're the two hard parts, and I will say something about relation to KdV, and I won't talk about existence, so I'll put that here. So hardly. So that so the idea of the proof. So the existence, I consider spin structures. So some line bundle S, that's a spin structure, its tensor S squared is the canonical. And then I'm going to take a bundle over, so I'm working now over a 2 to the 2G cover, the moduli space of spin curves, a bundle with fibers given by the joule. So this V, I mean the joule. So I'm going to take the joule of the spin bundle. So usually when one takes R spin or spin and produces a cohomological field theory, you use the spin bundle. I'm using the joule of the spin bundle. And what occurs nicely here is a bundle. Whereas for R spin and spin, one needs to work harder. So this will give me a bundle with fibers, and then I will take theta gn will be a push forward. I need a new so I've got this moduli space. So let me just give it the name. So capital P, a push forward of a top Chern class. So this is a bundle E of E, where this is the mapping from the moduli space of spin curves to the moduli space of curves, a degree 2 to the 2G map. But I'm not going to talk about distance. I will give rather elementary proof, but I find it to be a bit insightful, of the second statement. Okay, so the proof of the degree constraint. Now this is elementary. That's one reason I'm presenting it, because we can understand it very easily. But I also claimed before that there's basically two interesting classes out there. The trivial class, the identity that is, the number one, and this theta gn. And so in this proof of the degree, we'll see this. Okay, so let's set the degree of theta n to be equal to dg of n. So this is the degree. So now I have this condition here. Rho pulls this back, so I get from this, maybe I'll do this picture again. From this picture here, I get therefore d of gn is equal to d of g minus 1 n plus 2. But that means that dg of n is a function of, what order do I want to put these? Yeah, of 2g plus n. 2g plus n, 2g plus n is preserved, and I want to make it a function of 2g minus 2 plus n, the same thing. Okay, and so then now my next pullback. I mean, what I'm using here, of course, is the assumption that I have a degree. Pure degree. If I don't have a pure degree, for example, if I take the cut product of this with the Hodge class, I will get something else that satisfies this. I should, while I mention the Hodge class, point out that this genus 0 class being 0 is different to the Hodge class being 1. It's this type of trivial. There's no Hodge class similarity here. Okay, so now when I glue these together, what I get is that f of a plus b is equal to f of a plus f of b. What I've simply said is that the Euler characteristic of this guy without the node, if I put back an annulus back there, is equal to the Euler characteristic plus the Euler characteristic, where by Euler characteristic I mean subtract these points. Which means that this is, just iterate this, this is just a multiple of f of 1. Okay, so now that what that tells us is that dg of n is a multiple of 2g minus 2 plus n. So I'll put this up here. And there are only two multiples of 2g minus 2 plus n. So what we got from this, so d of gn is a function of 2g minus 2 plus n, which is 2g minus 2 plus n times f of 1. So we get that dgn is equal to k times 2g minus 2 plus n, where this k is standing for f of 1. And now the dimension of the moduli space implies that k needs to be 0 or 1. And therefore it's 1 because by condition 4 or 3, I don't actually need all of these conditions to prove this. This is by condition 4, it's 1. Okay, so that is, the degree is necessarily this. Okay, so notice that if, this is an aside, if we'd chosen k is equal to 0, this is saying that the degree is 0, and this is saying that theta is the trivial class. It could be a multiple, but we can rescale. This with k equals 0 implies theta g n is equal to 1. And 1 is the other class that satisfies this. So these properties here distinguish two classes. So there's something important about this class theta gn. In terms of, there's a question asked about Giventhal decomposition. In terms of Giventhal decomposition, it uses a whole lot of factors of KdV. Well, this Bresengross-Witten should be one of these factors. So it's a fundamental factor. The factors of KdV are corresponding to this cohomology class 1, and the factors of Bresengross-Witten are corresponding to these. So it's the same reconstruction will work.
So this theta 1 equals precisely 3 times psi 1 is needed in some other place.
Okay, so this was needed in existence. So I've defined some bundle here, and I need to calculate in 1, 1, and that's the, oh sorry, it arises in two places. It arises in my construction, but it also, if I don't use 1, 1, it ends up that I can produce, I've said that these intersection numbers uniquely determined by 1 to 4, so I could put, say, a lambda dependence just here, and I'll get all of these numbers depending on lambda, and they no longer give rise to solutions of KdV. I don't know that they exist, and their numbers aren't as good. So that 3 arose, I guess you could say, because of Bresengross-Witten, but in the construction, it arose. So the way to construct this in general, if I put a lambda there, is just to start at, it's easy to get the theta 1, 1, and then to try and do it in genus 2, but what you're looking for, if we think about the dual, we're looking for some special curve, or we're looking for a fourth cohomology class. In any case, one can do this in genus 2 because the cohomology is completely understood. Okay, so now the proof of KdV, but I promise that anything that needs to be seen should be more central, so someone needs to go. So it's something I've just written up there, I'd say. I want this formula to stare at us still. So maybe I'll still do it here though. Okay, so 3. The proof of the KdV relation uses Pixton's relations. And I'll try to get across this idea in a simple case. These were proven by Pandarapande, Pixton, and Zwonkine. So Pixton's relations are, and I'll give you an example of this, are relations amongst cohomology classes on the moduli space of stable curves. And so I'm going to, well, need that to understand something about this class theta. Oh, yeah, right. So right now I'm not going to use the construction. I'm just going to use just these properties. Yeah. And then, like I said, it will fail unless I have these. But right now I'm not using the construction. So I should say something, yeah, about this. It's sort of related to, I have no idea why it satisfies KdV. So the idea is to prove that this function, when I start with this theta class, and now I produce this, what I'm calling Z sup theta, I need to show that it's the same as Bresengross-Witten. So I compare it to a class, to a function which I know is a tau function of KdV, but I don't know why this one's a function of KdV. So that's the way this proof should work. I need to prove that Z sup theta is equal to the Bresengross-Witten. Okay, so here's an example of a Pixton relation, which is Mumford's relation. Yeah, I'll explain what this gamma 1 is. Gamma 2. So gamma 1, I won't write it. It's referring to some graphs, but I'll just say what it's referring to. This is what gamma 1 is referring to. It's referring to the divisor inside M2 bar given by essentially M11 cross M11. And gamma 2 is referring to this. Actually, it's referring to the dual graph, this gamma 1 and gamma sum 2. And so what this statement says is the first kappa class, that's an element of H2, is a linear combination of these classes defined by these boundary divisors. And so this is one of the earliest Pixton relations. And it's Mumford's relation, known by Mumford in his Towards an Enumerative Geometry paper. Okay, so this is now a relation amongst these cohomology classes. So cup this with theta 2. And then I'm going to integrate over M2 bar. So theta 2 next to kappa 1 is equal to 7/5 I'm going to take n to be 0, but I'm going to. So it ends up that this object that I constructed, I didn't, I guess, state it. So g is greater than or equal to 0, but g equals 0 is boring, and n is greater than or equal to 0. So all of these classes exist for n equals 0. This pullback relation, of course, tells me I'm only interested in the n equals 0. I've got them all after that. Okay. But here I'm actually going to convert rather quickly to M21. Okay, so let me just write this out and then make some comments about what I've written here, including the automorphisms. Plus, I guess I can read this, plus 1/5, 1 on the order of the automorphism group, the integral over M12 of theta 1, 2. Okay, so it ends up that this moduli space here, this divisor inside M2 bar isn't M11 cross M11, there's automorphism. So I need to divide by, well, 2. I'll continue this sentence in a moment. And similarly, it nearly looks like M12. It is a map from N12 bar into M2 bar, but it's actually, these points are not labeled. So I need to divide by that symmetry. And so, again, I'll get a 1 on 2 there. And now this, by assumption, is 1 on 8 squared. That's this assumption here. So the integral of psi 1 is 1 on 24. So that's And this is, again, the automorphism group is a half. And this one's also 1/8. So this uses this pullback relation. So I'm just let me say that I can calculate from my assumption on M11 bar, I can calculate this guy. And this is equal to 3 on 128. And so what this produces is this. So I've told you that because of this assumption on theta 1,1, I can actually calculate all of the genus 1 using this pullback relation. So theta 1n comes from a pullback of theta 1n and theta 1n minus 1. And so that actually produces all of these terms here. And similarly, just this calculation, I need to do one more thing to this calculation to convince us. This 3 on 128 can now be used to get all genus 2 terms. And one thing that's different about this to the Kontsevich-Witten is that there are only finitely many non-T0 terms for each genus. But that's just to do with the dimension, the degree of the class. This class here, because of my statement here, where I've taken a T1, this is actually, the first term here is 3 on 128 T1. T1, that encodes a psi1 class sitting inside M21 bar. And I've given this in M2 bar, but this is equal to the integral over M21 bar times psi1. So I won't do that calculation, but again, well, I'll say it verbally, it uses this pullback. And so what I do is I can pull back the map from, I can pull back this class. I get a psi1, but now I've got 2 psi1s. In that pullback I had a psi1, so psi1 squared, this is going to push forward to a kappa 1. So in any case, this is now giving me the coefficient of T1, so this is 3 on 128. So what I haven't, what I've hopefully done just then is convinced you a little bit that this is giving Bresengrose-Witten, but what I haven't actually shown you is how the proof works. And so the way the proof works is that what we have here is that this class here, this intersection number, and these intersection numbers satisfy a relation. It's not linear. This one's linear. This is quadratic. This is linear. It ends up that the coefficients, the corresponding coefficients of the Bresengrose-Witten free energy satisfy exactly the same relation. And what I need to do is I need to show this for all of Pixton relations. And so then what that requires is for me to go into obviously the construction of Pixton relations using A2 singularity. So the only thing I'll say about it is Pixton relations come about by Giventhal reconstruction, building cohomology class in the moduli space. And for example, for the A2 singularity, this cohomology class has just a degree that's not as big as 3g minus 3 plus n, and there's this space where there's no cohomology classes above. But the Giventhal reconstruction populates these spaces, and so these give relations. Something is equal to 0. So what's happening here is I get vanishing in these. The vanishing of something is telling me about some relations, and I get vanishing in 2 ways. One, because I know about the degree of cohomology classes. So this theta 2 is mapping strictly next to this. This is one of the classes that will, a Pixton relation. So I know something about this degree because it's a degree of a cohomology class times a degree of a cohomology class. The second, and so I get some vanishing, some high order guys vanishing. The second vanishing I get comes from the Bresengrose-Witten coefficients, and that uses topological recursion. So I can use topological recursion to check a whole lot of coefficients vanishing, and that's exactly, this vanishing is exactly going to be telling me I have the same relations. And I'm going to do this on the A2 singularity curve, which produces all of Pixton relations. And then I use the fact that Pixton relations will determine this uniquely. So that's a sketch of this. And so now the last, am I at 5 minutes? Is that right? Okay, I'll just mention something about Gromov-Witten invariance. Okay, so this class theta Gn now sits nicely next to cohomological field theories, which I won't describe. I'll just mention Gromov-Witten. So Gromov-Witten invariance of a target variety X. So I'm going to say very little about this, just because I've only got 5 minutes. So what I'm going to do, instead of saying much at all, I'm just going to give a very famous formula, so it'll be at least understandable because it's famous. So, and in the process, I'll make some remarks. So the MGN beta is the moduli space of stable maps of genus G curves with n-labeled points of degree beta. Beta is an element of H lower 2 of X. This has some unexpected, this moduli space has some components with unexpected dimension. This virtual class is a class with a nice degree. And so the famous formula is that this is equal to the dimension of X minus dimension of times 1 minus G plus the degree paired with the first Chern class. And this is famous because of the case when the dimension of X is 3 and C1 vanishes. That's Calabi-Yau. If we then choose n to be 0, this space has dimension 0. So look, that's as much as I'll say about these, just so that I can sort of be efficient here. So the idea now is I take this virtual fundamental class and I push it forward to MGN bar. That's one way to calculate these guys. So I'm not pushing forward the dimension, just the virtual fundamental class. Push this forward, I get some class there, and so what I want to do is I want to take the cup product. Well, let me actually do this for an example. Well, maybe I'll do it twice. Okay, so I want to take the cup product of this push forward and more generally I want to push forward, I'll push forward something more general in a moment, a pullback of some classes on X, and integrate these against psi classes and get some different Gromov-Witten invariance, say Gromov-Witten invariance twisted by theta. Again, I want to put up something easy here, and so now if I was to take the Poincare dual of this class and pull it back to this space of stable maps and intersect it with a virtual class, I get this. And so this is much easier to read than what I'm saying there. So this is now equal to the dimension of X minus 1 times 1 minus G plus C1 of X beta. So some things change. It's independent of n, and also the dimension that stands tall is 1. And in particular, elliptic curves seem rather important. So these invariants for elliptic curves, well, it's doing some counting. So what I'll do is I'll just say something about the case when X is P1, because I can calculate it, and it's also interesting. Okay, so this class, theta Gn, because of its properties, I think did I lose the properties here, it makes it calculable. So in particular, I'll take this object here. So this is sum over everything in sight. This push forward now of this class MGN P1 of D, virtual. Okay, thanks. And so it ends up that this is equal to Z sub n, where H bar is n to the negative 2, which is known as the Legendre matrix model. So negative 2 to 2, negative 2 to 2 dx1, dxn product I think I got it all. So what's interesting about this is, one, it's an exact formula. So when I assemble these Gromov-Witten invariants in H bar, this is actually the asymptotic expansion of an exact formula. This has been well studied. It's this. Let me just maybe just finish with one statement. What I can do is I can add descendants. So this will produce all the descendants via this matrix model. Will produce all my. I haven't described too much about Gromov-Witten, but it'll produce, for those who know, descendants using resolvents. But in this model here, I can also just put in just a little bit more. I want to now pull back the push forward, the pullback of the evaluation of the Kähler class. So this lives inside H2 of P1. And this push forward is for all of this. And then here, I want to put in this extra term, sum of the xi's. So in the matrix model, this would be the trace. And now this satisfies Toda. So satisfies, which is true of Gromov-Witten of P1. And so in this case, well, one way to write Toda in this case is, but the point of this story that I'm telling you is it's calculable because it's so well behaved. I'll finish that.